All right, again, welcome to Mplant's Paper Club. Today, we are going to talk about a paper which compares causal decision-making against causal effect estimation. I never thought about these differences before, but it's actually quite interesting to look at them. I'm going to share my screen so we can look at the paper. Share screen here. Good. Let's check if anyone new joins, so I can give them right to talk. No, just us. Cool. So the paper really is almost not ML, but more of a applied statistics. The question is causal decision making and causal effect estimation, are they the same thing or not? So we have had papers about causal effect estimation, particularly the Kate concept at Paper Club before, but that was a while back. So what we want to discuss today is that how important it is to have a statistically accurate causal effect estimation to make good decisions. Most examples in the paper are from marketing, really, but the concept of causal effect estimation is actually very generic, and we probably can extend this also to whatever is relevant for your work. Okay, so let's start with the abstract quickly. So first of all, the paper was published in a very new journal. I found it because I was looking into this journal. It's from Informs. Well, Informs is a society for operations research and management sciences, the biggest one in the world. So this one is Informs Data Science. It's a new journal about operations research and management science and data science. Okay, so it's not a very technical, deep ML, which we usually do here, but not always. Cool. So the abstract. So we're going to study, really, this is a review paper. We're going to look at lots of examples during the last 20 years, even 10, 20 years, that study causal decision making and causal effect estimation. Okay, and the findings are actually very interesting because they suggest that we don't need very accurate causal effect estimation to make good decisions. I'll go into details later on. And also, there were some examples that introducing bias in your causal analysis can actually help to make better decisions. Plus, sometimes more accurate causal effect estimation can lead to worse decision making. Those are kind of counterintuitive statements, and they may even seem wrong. They use the word wrong in quotations, as you can see here a few times in the paper, but actually there is a lot of justification for this. Okay, any comments so far?
No, that's good. Thank you.
Cool.
Question was maybe on the phrasing, whether it is helping or whether it is not making it worse.
Yeah. Yeah, well, I don't know, but yeah, fair. Cool. So let's look at this causal analysis idea, right? Simplest example is, let's say we have a company that sells paints, or credit card company, any sort of company that has lots of users and has to decide which ones to target, right? The real goal is that we can have formulate two problems here. One is, the causal effect estimation. Let me try to get this right. Causal effect estimation. So the idea here is that can we find statistical significance in accurately estimating the causal effect of treating a given customer or not, right? Like an A/B test. Do we give them an offer or not give an offer? That's what treat means. And the goal of causal effect estimation is to estimate the effect of treating or not treating the customer, right? But it does not necessarily, I highlighted it here, it does not necessarily, it's not necessary for it to accurately assigning treatments to maximize causal effect, okay? So causal effect would be the customer signs up, well, pays more than they would otherwise, okay? That's what the causal decision making is about. So here, our goal is to decide whether we treat this customer with the goal of maximizing some metric, such as paying more. Okay? We'll look at the mathematical formulations in a moment, but does this make sense? Did I get it right?
Yeah, that makes sense.
Yeah. Okay. So it seems like these two should be really the same thing, right? If you can estimate which treatments, like if you have a good probability distribution of the effect of your treatment on each customer, that should lead you to having good decisions. And if your probabilities are not good, you will make bad decisions. But actually, not always. We'll see soon. So there are a few more examples here, like
I think also you're a bit careful, right? So it's not that doesn't work, right? Actually, they say if you had that down right, then it would definitely be true, right? If you know the true effects, then you can always also find the best decisions. It's just that
yes, the problem is you can't always say that, right?
Yeah, this is more a practical issue, just because you never have enough data. That's
yeah. They will get to these issues also, because sometimes you can't run A/B testing. You can't say, well, let's see which employees tend to stay in the company by firing half of people and then not firing the other half, right? Sometimes you can't really run the experiment. Other times you run the experiment, but the results can be biased. But we'll go into these cases. But yeah, exactly. So if you have all your data points perfectly right, you should be able to also make good decisions. Thanks, Arvid, for that. Yeah. Okay, so there are a few examples here, which maybe we can skip for now. What I wanted to look here is, sorry, my computer is slow. There you go. Oh. All right. So this paper has three main contributions. I'm just reading the part on the right here. They want to highlight these three main points in the relevant research. Okay, one is we should carefully consider objective functions for causal machine learning algorithms. So this means that the objective functions you choose may also have an impact on the usefulness of the causal effect estimation for decision making. There's another interesting part, confounding. There's a chat message. I have just worked out why I couldn't get into the meeting this week. Oh, that's fine. I think maybe I'll mute and this. Is there a raise? Was there a raised hand?
Yeah, Vahan, can you hear me?
Yes.
Yeah, so just very quickly, I don't want to interrupt you.
No,
So
that's fine. Always interrupt. We want that. Yeah.
You've got two links on the meetup page. So one in the text, which works, and then there's one that's, I think, auto-generated by Meetup.
Oh, I see. Okay, good. Thanks for telling them. Right so after this, I'll go fix that. Yeah.
Yeah, please, because I last week I missed last week's talk and I kind of really look forward to it. So just for your information. So yeah, that's it. That's all I wanted to say.
Okay, thanks. Because the link expired, we made a new link. There's a chance the old one remains somewhere in the comments. I'll go clean it up.
Okay, thank you.
Sorry about that. Right. So as I was saying, the three contributions. The second one is confounding has different effects on causal decision making and causal effect estimation. It can help decision making, but it can create worse effect estimations. So confounding is about causal biases. So for example, if you target in your causal effect estimation, if you target only users who are likely to renew their subscription anyway, you are creating more specific, more biased causal estimation. But actually, for decision making, as we'll see later in examples, may benefit from that. Another suggestion that the paper makes is that that causal statistical modeling, getting good probabilities for causal effect estimation, may not be necessary for good causal decision making. Again, we'll see some examples later in the paper. Okay, these are the main 3 points that we discuss. Cool. If there's no comments, can continue. First, I want to make clear the differences between effect estimation and decision making. Kind of spoke about this, but let's actually make it formal. So down here, formula 1 is for causal effect estimation. So if we assume yi, which is a rational number, real number, is the potential outcome associated with a treatment I. So treatment, as I said before, can be target the user or not target, or it can also be non-binary. Okay, so I is an input, and y returns the potential outcome. Okay, so the causal effect estimation is the tau here, where x is the feature of a given user, and then the causal effect becomes the expectation given the feature of the user, or the expectation of the error, of the difference between applying the treatment or not applying. Okay, so here this is only for the case when we have a binary decision, 1 or 0, but you can also extend this to a more general case to have it over all possible treatments. Okay, this gives us the expected result of applying treatment or not applying treatment, treating the user or not treating the user. Okay? On the other hand, causal decision making is, well, is the action of treating users for whom the causal estimation is positive. Right? So this is what the formula 2 is saying. So because formula 2 depends on causal effect estimation, it's very normal and expected to assume that to get good decisions, we need first to get good probability estimations, taus here. Okay. Well, actually, tau also depends on a threshold that we decide, but we'll talk about this also later. Okay. I think this we can skip. So that's the thing about journal papers. There is a lot of detailed explanation, which we don't always see in conference papers, which I like. But we can skip a lot of the explanations here, unless there is a comment. I think it's fine. Let's go down to look in some differences. So why does it matter to have the estimation and decision making distinguished properly? Okay, so here's a very interesting example here. First, let's define the error, and then we look at the plot here. So first, we define the mean squared error for our causal effect estimation. Oh, one moment, give Newton this. Let me allow to. Cool. Right, a mean squared error. So the mean squared error over our estimated tau hat would be the expectation, well, for the error, right? So the mean squared error here, well, which is minimized if we get the tau hat perfectly right. Now, let's look at the figure on the right, where tau hat is our prediction, tau is the true effect, and we have two models. Okay, model one gets the mean squared error very wrong. So you can see the distance is very far here, right? But because for both cases they are positive, we always take the same action, which is treat, right? Because our prediction has the same result as the true effect, because they're both positive. On the other hand, model 2 has a much smaller mean squared error. However, while the truth is to treat, our model will say to not treat. So the action, the decision is wrong. Okay, just one example where it's possible to have much worse causal effect estimation for the right decision. On the contrary, we can have a very accurate causal effect estimation for the wrong decision. Problem being, we can't actually observe the true probabilities. The true tau, it's very hard to observe. Another reason why tau is hard to observe is because you often have only one observation. It's hard to get enough observations per user to have a true distribution for that user. So consequently, it's hard, if not impossible, to get the true effect for tau. So we always have some sort of estimation for it. So there is always an error in most practical cases. Okay. So this leads us to thinking as classification versus regression, or probability classification versus probability estimation. So basically, classification means positive or negative. We don't care how positive or how negative our estimation is, but we just want it to be in the right class. Right here, it's only binary, but in general, you can have multi-class classification. So if you focus on getting the probabilities right, kind of becomes a regression setting when you need to get the mean squared error minimized and the actual value right. Okay? So they have this comparison here between effect estimation and decision making as a probability estimation and classification. Any comments here? I was talking for a while. Okay. Right here, they also talk about another metric, which is the expected regret, which is defined based on the action, not taus, but the action directly. Okay, which is, so if A star is the best action, A hat is the evaluated treatment assignment policy. For example, it can be the one we defined before using the causal estimation, but not necessarily. So the regret is defined as the expectation over the difference between treatments as the best possible and the one we get, right? But they are also arguing that the regret is a good alternative for objective. I think we can skip those. They mentioned what I just said, that we can look at this as a classification problem versus probability estimation or regression.
Do you know how one would train such a thing in practice?
Train?
Yeah. How would I, build an objective function that measures or that minimizes the regret? That seems slightly non-trivial.
I agree. That's one thing I've been thinking about also. I was like, well, maybe we shouldn't care too much about probabilities, but actually do actions. But how do you actually train such a thing?
Exactly.
One idea is that, so let's say you have a machine learning model that gives a result, right? What you do is you put it under an optimization setting. They discuss that here also. They refer to a paper that did that. So you put your machine learning model into an optimization formulation where you optimize it for inputs. Okay, so you change the input, the trained model's outcome changes. So the model is pre-trained for whatever. Can also be the probabilities or any sort of objective. But the goal is that once you have a trained model, you put it under an optimization algorithm where you optimize over the inputs, and the optimization's objective becomes maximizing your reward or minimizing the regret, because now you have this a hat here as the variable in your optimization model, not the machine learning model. Does this seem meaningful?
So you would vary A star?
No, you vary a hat, A star. You don't know, right?
But you would evaluate it using the model you have trained in the first instance.
Mm-hmm.
Yeah, it's you would wonder why is it very different from calculating tau in the first place, or estimating tau. Yeah.
So so you mean your ML model already relies on tau?
Yeah, that ML model doesn't necessarily predict tau, right? It might predict something else that it might be more interesting, like whether I don't know whether this particular treatment is the best or which treatment is the best.
So I would say that you have the ML model, you train it to accurately have the end effect given an input, not to find the best treatment.
But isn't the treatment an input? Yeah, but you're right. Yeah.
So the input is, well, yes, the treatment is the input, but you optimize that using another layer of optimization algorithm, which can also then take into account any other constraints you may have. For example, you have budget constraints. You can't treat everyone.
Yep.
So they refer to another paper here that studied that. Maybe it's this one. Fernandez Luria, but I can actually find which paper it was. Just if you're interested, there was a paper that studied the optimization part of action of treatments. Cool.
Yep.
Yeah. Okay. Okay. Let's see what we have next here. I'm trying to make sure to not miss anything. I think that's all for this part. Yes. However, empirical evidence shows that the gap can persist. Oh, right. So to minimize the never mind. We spoke about this. Now the training data, right? How do you choose the training data? They talk a bit about biases here, and let's find that. Oh, here. Without going into the text, let's just discuss this plot because that's where discussion is leading to. So we have 3 cases here. Okay, we are studying 2 models: biased model and unbiased model. So unbiased model is always the same, right? It has seen the same data. There was no picking of specific users to train your estimations. Okay, same distribution. On the other hand, we have 3 different biased models. Okay, so biased models can happen. Simplest cases if in your model you look only at users that would buy your product regardless of treatment, or wouldn't buy regardless of treatment, right? Then your estimation is inherently biased. The question is it a bad thing? When is it a good thing? When is it a bad thing? So here we have tau, the causal effect estimation, and we have the delta, which is the threshold. I think it was 0 for our case before. Now, the 2 models have different distributions here, right? So on the left, A has biased model that's actually much worse than the unbiased model, because the unbiased model says, well, you need to treat, and in most cases you would treat, right? Most of the distribution is right from the delta. But for the biased model, it's not the case. We assume that the correct answer is to treat. In B, it's actually much harder to say which one is better, because they seem like equally right, equally good. And in the C, the opposite, biased model always says treat, which is the right thing to do. Now, the question is, should we sometimes aim to collect, to build biased models? Well, the answer isn't obvious. I mean, we can't just say, yes, always get biased model. You don't know which one you get, right? But if you know the bias, you can introduce it to your modeling. It's not uncommon to have inductive biases in your models. So maybe you can also benefit from additive bias in your data. If you know that all your clients that you are going to target in this campaign are from a specific age group, maybe when you do your study, only include the specific age group, right? It can help. Also, they argue that it's hard to collect enough data from everywhere to train models. We may have enough data to assess model performance, but not to train. So sometimes we are actually limited to biased, limited data. So we just need to be careful how we collect the biased data. Comments here? Okay. Oh, I don't have my notes here anymore. Then the next part goes over discussion to end up with this other plot. So here they study two models. One is by a causal model, the other one is a non-causal model. So those are three models. And the idea is that that sometimes non-causal models, a decision tree, can produce at least as much benefit as causal models. So this matters because sometimes we want to find alternative objectives that are not necessarily causal for the treatment. And it's not uncommon to do that. Simplest example, very commonly successfully used. Instead of measuring purchases on a website, people measure website visits. That seems to work, right? So visiting doesn't necessarily mean you will buy, but it's a good alternative measure where you have more data. So here, well, the dotted line is just a random targeting. Obviously, it's linear with 45 degrees here. So the x-axis is the percentage of population targeted. So the more population you target, the costlier your targeting is. And then y-axis is the conversion rate. Okay, so as you can see, well, if you target everything, you get the maximum conversion. In this case, it's 0.3% or so. All three models get that. But the important thing is how fast the conversion grows. So these two are similar, but the decision tree can actually be better, non-causal model, which they find interesting, maybe surprising, that sometimes simpler objectives can produce at least as good results. Okay, they talk about some more studies, but I guess we can move on. Future research. Well, paper claims that, by the way, a lot of the references in the paper were from at least 10-year-old papers, like this one, 2011, 21, but some are also new, right? So they try to give an overview of how causal effect estimation compares to causal decision making. And they're arguing that we should focus more on causal decision making. And they hope that they have introduced a new research direction for that. Next research steps they want to study is creating mathematical models that understand when causal decision making can be done without accurate estimations. We saw examples, but there was no actual mathematical modeling there. I think that's all. Oh, another important thing is that we spoke briefly about randomized experiments and in terms of bias, right? Because the only way to avoid or minimize bias is to run randomized experiments. But then we also found cases when maybe we want the bias. So they also clarify here that they want to make sure that they want to be clear that randomized experiments are important, and they are not saying they shouldn't be done, but they just have an observation that sometimes having the right bias can happen. I think that's all. Any comments, questions, anything I missed?
No, I think that's good.
No?
I think they, I like the fact that they point out at the back of they make pains at the end of the paper to say this does not mean that you can't make estimates of your, and that you don't need to try and make estimates of the size of the effect.
Yes. They try to be clear about that.
Also, the graph that you're on at the moment, if you target, say, 2% of the population, you're getting maybe double the performance than you would. A decision tree gets double the performance than a causal tree would. Maybe. Oh no, sorry, the graph doesn't start at 0. So okay.
No, it doesn't. It starts at 0.2. Yeah, because if you don't target anyone, some will still converge, right?
Yeah.
Cool. So I guess we can finish here. If anyone wants to volunteer for next week, let us know. Otherwise, we'll choose a more. Actually, next week we'll do it in person. I'll update the meetup page. So first, let's stop recording.